Welcome to EDU World Space.
Alright guys, we're doing problem 116 of chapter 9, Chemistry Essential Science. So the molecule 2-butene, C4H8, you can see the structure on the board, can undergo a geometric change called cistrans isomerization. As discussed in the Chemistry and Life box on the Chemistry of Vision, such transformations can be induced by light and are key to human vision. Where the hybridization of the two central atoms of 2-butene. These are these two central carbon atoms, and remember, if carbon's forming a double bond, then it's sp2 hybridized. So these are both sp2 hybridized. Now, for part B, the isomerization occurs by rotation about the central CC atom. With reference to figure 9.29, explain why the pi bond between two central atoms is destroyed halfway through the rotation from cis to trans isomerization. So we're going to go to figure 2.29. Sorry. And so the reason that we see color has to do with proteins called rhodopsins. These were us. So vision begins. So let me start from the beginning. Vision begins when light is focused on the lens of the eye onto the retina, the layer of cells lining the interior of the eyeball. The retina contains photoreceptor cells called rods and cones. The rods are sensitive to dim light and are used in night vision. The cones are sensitive to colors. The tops of the rods and cones contain a molecule called rhodopsin, which consists of protein opsin, bonded to a reddish-purple pigment called retinol. Structural changes around the double bond in the retinal portion of the molecule trigger a series of chemical reactions that result in vision. We know the double bond of two atoms is stronger than a single bond between two atoms. We are now in a position to appreciate another aspect of double bonds. They introduce rigidity into molecules. So consider the C-C double bond in ethylene. Imagine rotating one C2H group in ethylene relative to one other C2H group. So this rotation destroys the overlap of the pi orbitals. This breaks the pi bond, and a process that requires considerable amounts of energy. Thus, the presence of a double bond restricts bond rotation in the molecule. In contrast, molecules can rotate almost freely around a bond axis in single bonds because this motion has no effect on the overall overlap for a sigma bond. Rotation allows molecules with single bonds to twist and fold as if their atoms were attached by things. Our vision depends on the rigidity of double bonds in retinol. In its normal form, retinol is held rigid by its double bonds. Light entering the eye is absorbed by rhodopsin, and it is the energy of that light which is used to break the pi bond portion of the bond shown in red. Breaking the double bonds allows rotation around the bond axis, as changing the geometry of the retinol molecule. The retinol then separates from the opsin, triggering the reactions that produce a nerve impulse that the brain interprets as sensation of vision. It takes a few as 5 closely spaced molecules reacting in this fashion to produce the sensation of vision. There's only 5 photons of light necessary to stimulate the eye. The retinol slowly reverts to its original form and reattaches to the opsin. The slowness this process helps explains why intense bright light causes temporary blindness. The light causes all of the retinol to separate from opsin, leaving no molecules to absorb light. Yes. So that's why so to put simply, that's the reason the pi bond is broken when we do cis-trans isomerization. It's so that we can have that It's so that we can have free bond rotation when we have a single bond, and then we reform our double bond so we can move from the tris isomer to the trans isomer, because you can't do free bond rotation with your pi orbital. Sorry, you can't do free bond rotation when you have a pi bond. So based on average enthalpies, how much energy must be supplied to break the C pi bond and cause the isomerization. So we're going to show a reaction for the C double bond, and we're going to make us, so we're going to break our C double bond and form a C single bond. So it's going to look like C, C, 2, C, C. Yes. So but we're actually going to be a bit more detailed in this. So we're going to draw the structure of our molecule. So I'm just going to delete this right now to get some more room. Well, adding all of this up doesn't particularly matter because the structure of a molecule is not going to change. It's just going to change from a single bond to double bond to a single bond. We're going to use Hess's law. Delta H reaction is equal to delta H of products minus delta H of reactants. So we have our double bond. So the delta H is going to be delta H of our single bond. That's going to be be 348 kilojoules per mole minus 614 kilojoules per mole. Else. So that means that 348 minus 614 is 2, delta H is 260, is minus 266 kilojoules per mole. So that means the energy of our pi bond is equal to 266 kilojoules per mole. Thus, because that's how much energy it takes to break our pi bond and form a single bond. So now D was the longest wavelength of light that will provide photons of sufficient energy to break the isomerization. But first, I have to put this in terms of energy per. We gotta change the energy per mole to energy per molecule. 266 kilojoules per mole times Avogadro's number. 1 mole per 6.02 times 10 to the 23 molecules. So that's going to be 4.42 times 10 to the 23rd, negative 22nd kilojoules per molecule. So D, what is the longest wavelength of light that will provide photons of sufficient energy to break the CC bond and cause isomerization? So we have to convert this energy, and we're going to convert it to wavelength. So E is equal to hc over lambda. So lambda is equal to hc over E. So lambda is going to be equal to Planck's constant, which is going to be 6.63 times 10 to negative 34. Times 10 times 3 times 10 to the 8th meters per second over 4.42 times 10 to the negative 22nd. By 4.42 times 10 to the negative 22nd. As kilojoules. First, let me just convert this to joules per molecule. (4.42) times 10 to the negative 19 joules per molecule. So lambda is going to equal 3 times 10 to the negative 34 times 3 times 10 to the 8th divided by 4.42 times 10 to the negative 19. So lambda is going to be equal to 4.5 times 10 to the negative 7 meters. Gotta move this over. So lambda is equal to 450 nanometers. That's the longest wavelength of light that's going to break the CC pi bond and cause the isomerization. And so part B, they want to know is this in the visible spectrum? And yes, this is in the visible spectrum. Our visible spectrum is approximately 400 nanometers to about 750 nanometers. So this would be like the purple blue range of the visible spectrum. Yes. And because it's in the visible spectrum, that means uh, this explains like why we see in the visible spectrum, like why we don't see in the ultraviolet or the X-ray or infrared. It's because visible light is what's causing this isomerization, this cis-trans isomerization, and that's what's causing this chemical reaction. That's specifically why we can see in. That is explicitly why we can see. That's explicitly why we can see in the visible spectrum is because visible light is causing these chemical reactions in our eye, and that's what's causing signals to be transferred to our brain, and then we register that as color. It's because visible light causes the cis-trans isomerization. Interestingly enough, that's also why UV light will blind you, because UV light is so high energy that it doesn't cause cis-trans isomerization. It permanently breaks that pi bond, and then your proteins can't function properly, and they can't send signals to your brain. Here it is.